Right, welcome to the part 4 of special relativity and E equals MC². You will find all these videos on my playlist per just check them out. So, in the last video, that is special relativity and E equals MC² part 3, I have derived the equation for the relativistic Doppler effect. So, let's move further. Just imagine there's a vehicle which is moving in this direction at a velocity v, and there are two laser beams applied both sides of the vehicle, and both of them releases photon, and each photons have an energy equals to E. One photon here at the speed of light have an energy E. So you just know why this photon is closer and why this photon is farther away from the vehicle, because this vehicle is moving towards this photon and this vehicle is moving away from this photon. So just let the energy loss of energy, capital E, equals 2E. Why 2E? Well, the photon, this is a photon, both have an energy E. So using common algebra, high school algebra, we can just write E equals 2E. Capital E equals 2E. Now, as we know from Professor Max Planck's equation that energy is Planck constant times the frequency, E equals h nu, and by the equation of relativistic Doppler effect you'll get to know about the frequency of both the two photons. That is, of this photon the frequency will be nu times under root C plus V over under root C minus V, and the frequency of this photon will be nu times under root C minus V over under root C plus V, where V is the velocity of the vehicle and C is the speed of light. We know Professor Max Planck's equation E equals h nu, energy of a photon is Planck constant times its frequency, and we know that now we have to find the energy loss, which is capital E. That will be equals to the sum of both the two energy in energy form. So this, if you just multiply this frequency by the Planck constant, we will simply have the energy of the photon. So energy times under root C plus V over under root C minus V, and add it with this one. So we have to place the Planck constant here, and this will be the energy of a photon. So E times under root C minus V over under root C plus V. Moving further, we can just take E as common. E multiplies C plus V plus C minus V over under root C minus V times under root C plus V. This is the energy loss, and simplifying this equation a bit more, we will have E times 2C over under root C square minus V square. That is equals to 2E times 1 over under root 1 minus V square over C square. And as we know that 2E is the total energy, so we can just write it as E times 1 over under root 1 minus V square over C square. So remember one thing, that the person in this box is an S prime frame of reference. So the person in the S prime frame of reference will just say, according to S prime, energy, I'm just simply writing E, before emission is H naught, and S prime also says that energy after emission of the photon is H1. So we know that H1, that is energy after emission, will be equals to energy before emission minus the loss in energy, which we derived a few seconds ago, or a few minutes I suppose, 1 over 1 minus v square over c square under root. Now imagine two frame of reference again, S and S prime. So according to S, energy before emission is E naught and energy after emission is E1, and for S prime, energy before emission is H naught and energy of the photon after emission is H1. So according to S, E1, that is energy after emission, is equals to energy before emission minus the energy loss, capital E. And according to S prime, energy after emission is H naught, which is energy before emission minus E times gamma. Why gamma? Because according to this equation we have 1 over under root 1 minus v square over c square is the Lorentz transformation gamma, which we call gamma, and just multiply it with the total energy. So there's a difference between S prime and S perspective, and there's the difference because S prime is in motion. Because it's in motion, it have an energy which that is known as the kinetic energy. Therefore we can say that the total energy with S prime before emission, which is H naught, is greater than the total energy of S, which is E naught before emission. H naught is greater than E naught, and H naught minus E naught is equals to K naught plus B. B is a relativistic constant, non-relativistic constant So if you just subtract the energy before emission with S prime with the energy before emission with S, you will have what we call the kinetic energy, and this is the result before emission. Let me write it BE. BE means before emission, and the results after emission, I'm just in short writing AE, will be H1 minus E1, which will be K1 plus B, where B is again a non-relativistic constant, and the extra energy, the reason why H0 is greater than E or H1 is greater than E1 is because of this existence of kinetic energy, because S prime is in motion, so it have the energy of motion, which you call the kinetic energy. And I also want to tell you that both the two equations are not equal, because after emission, here in the equation of after emission, let it be equation 1 and equation 2. In the equation 2, which is after emission, the vehicle is losing some energy in form of the photons. So if you just subtract both the two equations, we'll have H0 minus E0 minus H1 minus E1, which is equals to K0 minus K1, and we'll just leave this be. And just moving further, we'll have H0 minus H0 minus H1 minus E0 minus E1, and that will be the change in kinetic energy. We'll write it as delta K. And if we get more precise, we'll notice that H0, energy before emission for S prime, minus energy after emission for S prime, that is the energy loss, which we have derived as E times 1 over under root 1 minus V square over C square, or in short E times gamma. And now we have to subtract this E, which will be equals to delta K. Why we have taken this E here? Because energy before emission for S and energy after emission for S again is simply the energy loss. Let me turn the page. I've written this once again. Now if I just take both the E as common here, we will have E times 1 over under root 1 minus V square over C square, and at this place we'll just, because we have nothing, so we'll just keep 1, which is equals to delta K. Now as we know that this gamma term 1 over under root 1 minus V square over C square is equals to 1 minus V square over C square to the negative half. We know this thing. If we just apply the famous binomial term 1 minus x to the power negative half, which is equals to 1 plus 1 over 2x plus 3 over 8x squared plus, and it goes further. So if we just apply this thing here, we'll just have 1 minus V square over C square, which is equals to 1 plus 1 over 2 x, which is V square over C square, plus 3 over 8 times V square over C square. And we'll move further. We're just gonna take this result, because this result and the results after this is neglected because it's too small. I'm so sorry for that. So we're just gonna take this one here, so it will simply be, we have to just E times half of this V square over C square minus 1 equals delta K. We can write it as E times 1 over 2 times V square over C square equals delta K. We know that kinetic energy is equals half mv square by the equation of classical physics. So E times 1 over 2 times V square over C square equals half m naught V square minus half m1 V square. Why we have taken m naught and m1? Well, m naught is the mass before emission and m1 is the mass after emission. By the photoelectric effect, we get to know that light sometimes behave like a particle. So let's move further. We can just simply C square, which will be half. We have to take both the 2 as common, I mean the masses as common, m naught minus m1. I'm so sorry, I mean I have to take the velocity squared as common, and I have to subtract both the 2 masses. So now we have to move further. We can just cancel both the 2, and we have something else. let me see, we can cancel v square and v square from here, and we're left with E equals m0 minus m1. Wait, we also have the c square, so E over c square is equals m0 minus m1. So we have to just take this as simply m. Let me write it here. So E over c square equals m, therefore E equals mc square. And this is the world's most famous equation, which describes the relationship between mass and energy. That means mass and energy, they both are equivalent, and we can just use them interchangeably. Thank you.